Prepare for a revolution in our understanding of the outer solar system, because the James Webb Space Telescope has just changed everything we thought we knew about Pluto. The moment its ultra-sensitive lenses were aimed at the icy dwarf planet, astronomers braced for data, but what came back was beyond anything they imagined. This wasn't just a better picture of Pluto. It was a revelation that forced scientists to reconsider long-held beliefs about the nature of our solar system's distant frontier. For decades, Pluto was the great mystery at the edge of our cosmic neighborhood. Located over 3.6 billion miles away in the Kuiper Belt, Pluto had always been a blurry enigma. Even after the stunning flyby by NASA's New Horizons mission in 2015, much about Pluto remained unanswered. But now, with Webb's cutting-edge infrared vision, we are seeing Pluto like never before, and what it's revealing is extraordinary. With its 6.5-meter gold-coated mirror and position in deep space beyond Earth's atmosphere, the James Webb Space Telescope has the power to detect faint heat signatures and subtle temperature changes invisible to traditional telescopes. Unlike optical telescopes that see visible light, Webb works in infrared, which allows it to see through Pluto's thin atmosphere and beneath its frozen surface layers. What it found there is astonishing. The new images showcase the intricate nitrogen ice plains of Sputnik Planitia, the massive heart-shaped feature that made headlines back in 2015. But Webb's advanced sensors reveal the kind of detail that New Horizons never could. Subtle changes in brightness and texture suggest ongoing surface processes, areas where ice might be sublimating or redepositing, evidence of possible seasonal cycles, and even signs of geological activity. That's right. Despite being a small, cold, and distant world, Pluto might still be geologically alive. And the atmosphere? Webb is offering an unprecedented look at its structure. Pluto's thin shell of nitrogen, methane, and carbon monoxide becomes far more readable in the infrared. Scientists are now tracking changes in its atmospheric pressure and thermal distribution, offering fresh insight into how the planet's environment evolves over its long 248-year orbit around the Sun. But it doesn't stop there. Webb also turned its gaze toward Pluto's 5 known moons, starting with Charon. Half the size of Pluto and locked in synchronous orbit, Charon has always fascinated researchers. Webb's data shows its surface is more complex than previously thought, revealing signs of frozen ammonia and complex organic compounds. Even its crust appears to have changed over time, hinting at a dynamic geological past. Then there are Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, tiny, irregular worlds that have long evaded detailed observation. With Webb's precision, scientists can now more accurately determine their surface materials, orbital paths, and even their potential origins. Each piece of this cosmic puzzle adds to our broader understanding of Pluto's evolution and the nature of the Kuiper Belt itself. What makes this all so groundbreaking is how it reopens the debate about Pluto's status as a planet. Ever since the International Astronomical Union reclassified it as a dwarf planet in 2006, arguments have raged on both sides. But now, with fresh data showing complex surface activity, a layered atmosphere, and potential subsurface oceans, Pluto is beginning to look more and more like a full-fledged planet again. Scientists are asking, should we rethink what it means to be a planet? More importantly, Webb's success with Pluto has massive implications for the entire Kuiper Belt. This icy region is home to thousands of similar objects, each holding clues to the early solar system. With Webb's unmatched clarity, astronomers are already planning to study other Kuiper Belt objects, KBOs, using Pluto as the first step in a much larger journey into the frozen edge of our Sun's dominion. And the more we learn, the more Pluto challenges our assumptions. For example, Webb's infrared imaging reveals changes in thermal emissions across Sputnik Planitia that may indicate subsurface convection, an internal churning of nitrogen ice that reshapes the surface over time. This suggests Pluto may have a differentiated interior, with a potential liquid ocean buried beneath layers of rock and ice. If proven, this could make Pluto one of the most exciting candidates for astrobiology beyond Earth. Pluto's active geology could be driven by tidal interactions with Charon, much like how Jupiter's moon Io is heated by its tug-of-war with Europa and Ganymede. This gravitational stretching and squeezing might generate internal heat, supporting the possibility of cryovolcanism, volcanoes that erupt with ice and gas rather than lava. Webb has detected features along Pluto's surface that may be cryovolcanoes, raising new questions about its interior dynamics and thermal evolution. Even the color variations seen in Webb's imagery hold surprises. Some regions appear redder than previously observed, likely due to tholins, complex organic molecules formed by solar ultraviolet irradiation of simpler compounds like methane. These tholins are considered building blocks for prebiotic chemistry, hinting that Pluto's surface might be far more chemically rich than once thought. Pluto also demonstrates seasonal variability. As it travels its long orbit, it undergoes significant changes in surface and atmospheric composition. Webb's observations reveal regions where frost is retreating and others where it is accumulating, offering a window into a frozen world that is anything but static. These seasonal changes are gradual on human timescales, but they provide crucial insight into how celestial bodies behave in extreme environments over centuries. Webb's capabilities also allow for long-duration monitoring, which means scientists can now observe how Pluto and its moons change in real time over months and years, not just during fleeting flybys. This continuous observation model will provide unprecedented insights into the life cycles of distant, icy bodies. And let's not forget the implications for exoplanet research. Understanding Pluto helps us make sense of the many exoplanets detected in cold, distant orbits around other stars. These frozen giants might have similar atmospheres, surface chemistry, and internal structures. In a way, Pluto becomes our local laboratory, a stepping stone to decoding alien worlds. The James Webb Space Telescope wasn't specifically built to study Pluto, but its success here is a testament to its versatility. Originally designed to peer into the early universe and explore the first galaxies formed after the Big Bang, Webb is now showing us that it can illuminate the hidden secrets of our own cosmic backyard. From Pluto's icy heart to its mysterious moons, every pixel captured adds depth to our understanding of the solar system. With each new observation, we're reminded that exploration is a never-ending journey. The James Webb Space Telescope has only begun to scratch the surface of what's possible. The mysteries of Pluto are unfolding not in isolated discoveries, but in a grand narrative of planetary science, geology, chemistry, and astronomy all intertwined. And so, Pluto stands not just as a dwarf planet or a reclassified oddity, but as a vibrant, dynamic world, an ambassador of the Kuiper Belt, a symbol of cosmic resilience, and a reminder that even the coldest, most distant objects in the solar system still have stories left to tell. Thanks to Webb, we're finally starting to hear them. And this truly is just the beginning. This is where the James Webb Space Telescope truly sets itself apart, not only in the kind of observations it delivers, but in how it enables scientists to ask bolder questions about our solar system. The high-resolution images of Pluto aren't just stunning, they're unlocking new avenues of inquiry that reach far beyond the icy dwarf itself. Suddenly, we're not only reconsidering Pluto's story, but the stories of other distant objects in the Kuiper Belt and even icy moons throughout the outer solar system. Astronomers are now turning Webb's instruments toward other dwarf planets like Eris, Makemake, and Haumea, each with unique features and mysteries that have been long hidden in the cold shadows beyond Neptune. Eris, slightly more massive than Pluto, could yield insight into differences in atmospheric retention at such extreme distances. Makemake, coated in suspected methane frost, and Haumea, with its rapid rotation and elongated shape, are just waiting for the level of scrutiny that only Webb can provide. These objects, once mere smudges of light in the telescope's eyepiece, now shimmer with geological potential and chemical complexity. They've gone from being dots to destinations. What's particularly valuable is Webb's infrared sensitivity to cold, distant bodies. Pluto and its fellow Kuiper Belt objects emit almost no visible light, but in the infrared spectrum they come alive. Heat signatures, chemical fingerprints, even faint geological movements emerge from the dark. Suddenly, the far reaches of the solar system feel less like a frozen void and more like a vibrant frontier. Each new observation sharpens our understanding not just of these individual worlds, but of how the entire solar system formed, evolved, and continues to change. And Webb's impact isn't confined to the Kuiper Belt. By studying these icy bodies in such detail, scientists are drawing powerful comparisons to the moons of the gas giants, and even to exoplanets light years away. Pluto's suspected subsurface ocean opens up tantalizing questions. Is it similar to Europa's or Enceladus's oceans? Could such internal reservoirs of water exist on exoplanets orbiting red dwarfs or hidden beneath the crusts of rogue planets drifting between stars? Webb doesn't just provide answers, it inspires new questions. If Pluto can stay geologically active this far from the Sun, what else might be stirring in the cosmic cold? In this way, Pluto transforms from a former planet into a cosmic keystone, a test case for understanding the potential for complexity in seemingly inhospitable places. With Webb's long-term monitoring, we're now watching as Pluto breathes, shedding frost, shifting its atmosphere, and perhaps even rumbling with slow tectonic forces beneath its icy shell. Seasonal patterns, driven by its 248-year orbit, are no longer theory, they're being traced in real time. The story of Pluto is no longer frozen, it's unfolding. But what powers this persistent dynamism? One leading theory points to tidal forces generated by Charon, Pluto's largest moon. Locked in a gravitational waltz, the two bodies orbit a shared center of mass, pulling and tugging on each other's crusts. This could generate internal heat, enough to keep pockets of water in liquid form beneath Pluto's frozen heart. And if cryovolcanoes exist, as some data suggests, they may be venting methane, nitrogen, or even ammonia from the interior to the surface, gradually reshaping the terrain in strange glacial eruptions. Webb's instruments are already offering evidence to support these ideas. Subtle temperature gradients and spectral fingerprints hint at a landscape in motion. This is no longer the quiet, inert Pluto imagined a generation ago. It's a place of shifting ice flows, atmospheric pulses, and possible subterranean oceans. And while we may be decades from sending another mission to land there, Webb allows us to listen in on its slow heartbeat from afar. Meanwhile, Charon is undergoing its own renaissance in scientific focus. For years, it was a blurry sidekick, always in Pluto's shadow. But Webb has changed that. It's mapping the distribution of ammonia ice and other complex molecules across Charon's surface, revealing scars from ancient impacts and possible cracks from internal processes. Some researchers believe Charon, too, may have once had a subsurface ocean, now frozen, but leaving behind geological echoes that Webb is starting to trace. The ability to compare these two worlds, Pluto and Charon, side by side with such clarity marks a turning point in planetary science. And Webb isn't stopping there. It's also illuminating the smaller moons, Styx, Nix, Kerberos, and Hydra, which have always eluded deep study. Now, with better orbital models and surface composition data, scientists are rethinking how these satellites formed. Were they fragments from a massive collision? Did they coalesce from Pluto's ancient disk of material? Webb is helping to reconstruct these stories frame by frame. This growing field of comparative planetology is one of the telescope's most powerful legacies. By identifying common traits and key differences among icy worlds, scientists are uncovering universal patterns that shape all planetary systems. For example, does Pluto's nitrogen cycle resemble the methane cycles on Titan or the oxygen-based cycles hypothesized on exoplanets? Are the organic compounds on Pluto related to prebiotic molecules found in comets or meteorites? These are no longer speculative questions, they're empirical ones rooted in real data. And yet, the most profound effect of this new image of Pluto may not be scientific. It may be emotional. Just a few decades ago, Pluto was little more than a phantom, a moving blur at the edge of the sky. Then came the 2015 flyby of New Horizons, and now Webb's crystalline gaze. Suddenly, Pluto is not only visible, it's relatable. Its frozen heart, its windswept plains, its lonely moons, they speak to the explorer in all of us. They remind us that no destination is too remote, no mystery too vast, if we have the will to look. This isn't just a win for astronomy. It's a victory for imagination. Every pixel of Pluto's portrait carries with it the fingerprints of thousands of people. Engineers, programmers, scientists, mission planners. The gold-coated mirror of Webb is, in a way, a reflection of humanity's desire to understand our place in the universe. That desire has sent our instruments billions of miles into space, and still further, into the hearts of galaxies. And now, into the quiet twilight beyond Neptune. As scientists dig deeper into the data, they're already crafting the next chapter. Plans for missions to Triton, Neptune's retrograde and possibly captured moon, are gaining steam. Triton shares many features with Pluto and may have once been a Kuiper Belt object itself. There's growing excitement around sending landers to sample surface chemistry, sniff out atmospheres, and drill into the crust for signs of life or geochemical processes. The Webb telescope will be the reconnaissance scout for these future explorations, pinpointing the places most likely to yield discoveries. At the same time, Webb is unlocking more mysteries of the solar system's edge. Sedna, with its extreme elliptical orbit, may be part of a population of objects influenced by yet undetected giant planets. Its reddish hue and faint surface signals suggest exotic organic materials. Webb may not have discovered Planet 9, but it's mapping the void where such a planet might exist. And every new image of an oddball orbit or a slow-spinning rock feeds that search, one faint signal at a time. And then there's the philosophical impact. The fact that we can see Pluto this clearly means we've crossed a threshold, not just of technology but of vision. We no longer stare into the dark with hope alone. Now we stare into it with understanding. The outer solar system is no longer a wilderness of static ice. It's a symphony of motion, chemistry, and change. This new era also reframes the question of what a planet is. Pluto may be labeled a dwarf, but its behavior, seasonal shifts, possible oceans, geological activity, suggests it's more dynamic than some larger planetary bodies. Webb's data will continue to add pressure to the debate, giving new weight to the argument that planet classification should consider complexity, not just orbit and mass. In this sense, Webb may someday be remembered as the telescope that helped Pluto earn back its planetary stripes, not through lobbying but through science. But for now, Pluto doesn't need to be reclassified to be revered. It's already proven itself to be a world worth knowing, and the James Webb Space Telescope has given it a voice we can finally hear. It's the cold whisper of winds over icy plains. It's the silent dance of moons in synchrony. It's the slow exhale of nitrogen into the vacuum of space. As long as Webb continues its mission, more of these whispers will become clear. More voices from the dark will speak. And we, with our ever-curious minds and tireless ingenuity, will be listening. Because the universe is not done telling its story. And we are not done asking questions.